So the trade-off with variance and bias is also related with overfitting and underfitting. So underfitting would be a low variance and a high bias. Yeah. So for example, if we use just the mean output as an estimator, which is a very simple model, we will have a low variance but a high bias. That's exactly the point here. Low variance, high bias. So the model complexity is low and we probably underfit. High bias means a model does not approximate the underlying function well, of course. Yeah. And that's what actually underfitting is about. Yeah. Overfitting would be the other extreme. That would be high variance and low bias. Yeah. High variance means the model is too complex, so small changes in the data cause the predicted value to change a lot. That is exactly what is meant when we memorize. Yeah? If we see a little bit of different thing, we memorize different things, which end up in we have a high variance. So that would be on this spectrum here. So we have here underfitting and here overfitting, and we of course want to balance this trade-off between underfitting and overfitting. So bias and variance can help us in finding a good balance between these two problems. Yeah. So searching for the best trade-off between bias and variance, we usually do different things. So in regression, we try to control the bias-variance trade-off by means of the polynomial order or the number of coefficients. Yeah. We'll see just in a minute how to do it. So regularization actually tries to balance the number of coefficients or the order of the polynomials used. Yeah? And in regression trees, we try to control the bias variance trade-off by controlling the tree size and the number of submodels. So regression trees meaning here these piecewise linear models. So how many intervals actually? Yeah? Polynomials, how complex is the polynomial? And regression trees or piecewise linear models, how many intervals, how many partitions do we have? The more we have, the higher the overfitting, the lower we have, the higher the underfitting. Yeah? That's exactly the trade-off that we have here and also here. Yeah? And that's how we control it actually. So how do we do that in the normal regression, so to say, or in the linear regression or polynomial regression? We do typically regularization. So the usual optimization goal of linear and polynomial regression is minimizing the sum of the squared errors. And that is in the basic regression model an unbiased model, yeah, with a very high variance. Yeah? So in that case, we have no bias, yeah, but a very high variance. And regularization tries to give up this unbiasedness and obtain a variance decrease by penalizing the model complexity. Yeah? So in linear regression, we can use linear regularization, which is also called ridge regression, which simultaneously minimize the sum of the squared errors as before, and in addition the norm of the coefficient vectors. And the coefficient vector actually, that is the beta here. Yeah, so that is the usual optimization function. So that is the prediction of the model. So that is the model, that is the prediction of the model, and that is the expected outcome. Yeah, that is the sum of the squared errors. Yeah, sum of the squared errors of the model, of the predictions, and the predicted values and the actual values. Yeah? We take the sum of the errors and the squared errors and the sum of the squared errors, and we want to minimize that. Plus now, and that is the regularization term here, plus the linear norm here of the norm of the coefficient vector, and the coefficient vector beta here, that is actually the model complexity, yeah? Because the model f here contains or is based on a coefficient vector, and the larger the coefficient vector is, the higher is the penalty, so to say. Yeah? So this is linear regression or ridge regression. The SU regression uses L1 norm here to penalize. So you see it's the squared of the norm here is missing. So it's basically the same idea. And both are actually working in the same direction. Yeah. So the basic idea here is that they penalize the size of the model, meaning the complexity of the model. Yeah? So the size of or the number of coefficients intuitively. Yeah? So that is the idea of regularization in regression, and that is really important in regression. So regularization plays an important point or important role in regression. So just keep that in mind. And of course, in statistics, that is a big topic because once again, regularization plays an important role here. Okay. So next up would be frequent patterns and association rules. That would be quite short here. So in that case, the patterns are frequent patterns, so frequently occurring objects or combinations. Yeah? So we want to determine the objects that appear frequently in data. Typically, frequently means that they exceed a given counting threshold. Yeah? And the objects that appear frequently are typically values or value combinations, which are called items or item sets, or also substructures like subtrees, subgraphs, or stuff like that. Yeah, so frequently occurring subgraphs or stuff like that. Here is an example for values and value combinations. So, for example, we want to know which objects, which values appear and value combinations appear frequently, appear more than, say, 4 times. Yeah? So, for example, butter, 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 butter. So butter is appearing more than 4 times or 4 times. The combination of butter and milk is also appearing 4 times, and so on and so on and so on. Yeah? So this is simply a counting thing. And that's actually why it's the simple kind of patterns, because we're just counting frequencies in that case. Yeah. Of course, the question is how to count more complex things beyond values or value combinations. So if you want to count substructures like subtrees or subgraphs or whatever. Yeah. Also, the problem is that the search space grows exponentially with increasing number of different objects. Yeah. It's just 2 to the power of the number of objects that are around there, and that can be really nasty. So different basic search strategies based on are around there, and they are also typically based on these monotonicity criteria for the counts. So there are depth first approaches like FB growth and breadth first approaches like a priori, and all those things are actually not heuristics, but they actually compute the real result, the non-approximate result. But since the search space has a lattice, a kind of lattice structure, but is still very huge, sometimes it's better to use depth first, and sometimes it's better to use breadth first search actually. Yeah? And there is an ongoing discussion which one is better under which conditions. Yeah, from these patterns you can get association rules. The patterns of association rules are frequent if-then rules. So you want to find all association rules like if X, then also Y. Yeah, with respect to a minimum support and a minimum confidence threshold. I think you all know these famous examples of of association rules. Is that people that buy diapers also buy beer, and you can extract that from these frequent item set results here. So frequent item set mining is a pre-processing step for obtaining association rules actually. Yeah, so the item set, the value combination diapers and beer need to be frequent with respect to this particular support. Yeah, that is the frequency threshold. And if this is frequent, then maybe also the association rule is frequent, so to say. Yeah, association rules can be derived from frequent item set, as I just said. Pay attention to negatively correlated item sets, because sometimes minimum support and minimum confidence of these association rules can be misleading, can be very high, but lower than the expected values, because the item sets are negatively correlated. In that case, it doesn't make sense to actually report these association rules. Yeah, just that you have a reminder. If you are working with that, you probably have to dig into the details again of KDM or of the textbooks. Last but not least, we have outlier detection. Just a very short overview here. As you see, the patterns here are now the abnormal objects. Yeah, so here is this famous definition of Hawkins, a statistician, that said an outlier is an observation which deviates so much from the other observations as to arise suspicion that it has been generated by a different mechanism. Yeah, so we have again this idea of a generating mechanism for our data, and then there are some objects that seem to have a different generating mechanism. Yeah, they have been generated by a different mechanism. There is a nice intuition by this case Hadlam versus Hadlam, which you may know about from KDM. So in that case here we have this observation of Mrs. Hadlam's pregnancy, which is 50 weeks instead of 40 weeks, and so this observation seems to not fit to the normal observations of all the other pregnancies in gestation periods of an hospital, which is the blue ones, and the green is so the Gaussian distribution of fitted to the observations here. Yeah? And this observation here, 50 weeks gestation period, does not really fit to this generating process here. So the assumption is that this has been generated by a different mechanism, different than Mr. Hadlam, so to say. Yeah? Okay, yeah, and outlier detection is usually unsupervised, so no information on the characteristics of the outlying processes are available. Maybe only about the data as an entire set, but we don't know what are the outliers, so we don't also know about the characteristics of these outliers. And that's why, like in clustering, many approaches are out there that have different basic assumptions about the characteristics of these outlying processes. Yeah? And that is the bigger picture here. That was everything for this week. Well, just I think more than two hours right now to metabolize for you. Also for me to metabolize. But anyway, so that was this part on the recap, and a little bit more than a recap. So next week we will start over with high-dimensional data, and that will be a big part actually, because we will talk a lot about high-dimensional data. A lot of things can happen actually in high-dimensional data, and we will find out what this is actually. Yeah, so it will keep us busy. This part will keep us busy, I think 2, 3, even 4 weeks or so. Yeah. So stay tuned, stay healthy. Hope to talk to you next week. See you there.